Okay, part B. Sorry, my video messed up the first time, so I have to kind of do this again, even though I've written all the answers down. But it's a short lesson, and I think I can still explain them thoroughly, and hopefully you can understand them. So first, key ideas. Um, so question, can we do these things? Is it allowed? Are we allowed to say the root of 25 times the root of 16 is equal to the root of 25 times 16? Yes. You're allowed to do that. You can combine two multiplications together into a single root, or almost more commonly, we actually go the opposite way, and we can break down a root into multiplications and then do them separately, and that's kind of behind most of our simplifications. And same thing works with division as well. You can combine those things together. So now the question for this section is, can I do this? The root of 25 plus the root of 16 is equal to the root of 25 plus 16. Is that allowed? And the answer in this case is actually no. You cannot combine these things together in this way. It's not going to work. And you can check this very easily. All you have to do is actually check these numbers. So the root of 25 is 5. Root of 16 is 4. So the left side of this is equal to 9. And then all you have to do is check what is the square root of 41. And the square root of 41 is, I think, 6.4. I did it earlier. I don't do that in my head. So it does not work. You cannot actually add these things together. And same goes for subtraction as well. That doesn't work either. That's not going to be allowed. And this is really the key distinction. This is something that I don't think I had clear in my head when I was going through grade 11 the first time. And it really made me scared to square roots because I was always kind of doing some small things wrong. If you can multiply and divide them, it seems weird that you cannot add and subtract them, but you're just not allowed to. Multiplication and division is okay, but the adding and subtracting, they just don't mix together. So what we want to think about every time we see them being added and subtracted from each other is throw back all the way back to grade 9 when we had like terms. That's really how we want to think about these all the time. It's just like a simplified root is like its own variable. So remember in grade 9, you could have, say, 4x's and 3x's. And the only time you can actually combine them together is when they look like this and they're like terms. In which case you actually end up having 7x's. And we like to use something for the variable like a bag of marbles. So we had 4 bags of marbles. We don't know how many is in the bag of marbles, but we have 4 of them. And then we gain 3 more of them. So in total we have 7 bags of marbles. You could not do anything with this one though. If you had 4a plus 3b, this will not combine together. It doesn't give you 7ab, it doesn't give you anything else. You just cannot touch them. They will not go together in any way. And it's the same thing with radicals. So radicals, once you've simplified it the way we did in the last section, you cannot add and subtract them together. You can't mush them together in any way unless they're like radicals. So examples of like radicals, 5 root 7 and negative root 7. These can combine together and you'll have 4 root 7. This one down here, 2/3 of something, 2/3 of a bag of marbles, and this is a whole bag of marbles. So if you combine those together, you'll end up with 1 2/3 bag of marbles, or 5/3 of the bag of marbles. But you cannot do anything at all with these two guys. And this is the real kicker. This is the one. Everybody sees this on the test the first time, and they think, oh, I should be able to simplify this more. My teacher's not going to be happy if I just leave it 2 root 5 plus 2 root 3. There must be something else I can do. But you can't. This one's just no good. It's done. You cannot go any further with it. That's like saying I have 2 bags of marbles and I also have 2 bags of candy. So what do you have in total? Well, you can't say anything else about it. You can't say I have 4 bags of candy. You can't say I have 4 bags of marbles. All you can say is I have 2 bags of marbles and 2 bags of candy. So think of a simplified root like it's its own variable at that point. It's untouchable. And the reason we want to think of it like a variable, the only thing that you could do is turn it into a decimal from there. But we don't like that. We're going to be doing it all with exact values. So you just think of it like a variable, make it untouchable, and then only use your like term rules for it. This guy, so the thing you want to pay attention to here as well is both of these were square roots. So it's not the square root that makes it like terms. These ones are not like terms anyway. And in this one down here, the thing on the inside is both 5a. But these still are not like terms. This is no good either. It's not the radicand that makes it like terms either. It's the whole thing. So this one has a different index than this one, so they are not the same variable. This is like an x and an x squared. This is like an a and a b. Neither of these combine together. The only time you can add and subtract radicals is if they're like radicals, and to be a like radical, you have to have the same radicand and the same index. So the whole thing in here has to look the exact same. Like this one was root and 7. This was third root and 5x squared. So that's what makes them the same. Okay, to simplify. So when we're simplifying, we have to do 2 things. First, we convert radicals to mixed radicals in its simplest form. So that's what we did in our last lesson. We pulled out numbers that we could pull out. And the reason we like to do this so much is because of what we just saw. Sometimes when you turn them into their simplest form, then you find like terms that weren't there before. So every radical would basically look different if you couldn't simplify it first. But after you simplify, quite a few of them will end up looking the same, because there's only so many different things you can simplify to. There is still a fair bit. It's probably not that likely in the whole world of things, but it's much, much more likely. Okay, so let's try a couple questions. So we have root of 50 plus 3 root 2. So we need to simplify root of 50. We remember that root of 50 is actually 25 times 2. So the 25 comes out, and it becomes 5 root 2. So this question is 5 root 2 plus 3 root 2, which simplifies just down to 8 root 2. This is like radicals, so we have 8 of them. Not too bad. Okay, this guy over here. Now we need to simplify all these terms down. So root of 27 divides by 9. So the 9 gets pulled out to the outside, and it becomes 3. It was 9 times what to get to the inside? Well, that also was 3. So this one is actually 3 root 3 when you simplify it with the negative still in the front. 3 root 5 doesn't simplify. The smallest number you can actually divide these by is 4. So root 5 won't be able to go any further. Reason being that number 1 up on that board, it doesn't actually help you. You can pull out 1s till the cows come home. It's not going to make anything simpler. That's what we call the trivial solution. So you can pull out 1s, but it doesn't actually affect anything. So the smallest is a 4, so it doesn't help. Root of 80. So you could divide this by 16 is the best possible number. So it's actually 16 times 5. And 16, when you take the square root of it, is 4. And the 5 stays on the inside. Now, I think Jardine was asking what happens if you do this in 2 steps? What happens if you don't know that it's dividable by 16? You might say instead that I can divide it by 4. So let's actually just do that real quick. So root of 80, the first thing you'll tell me is it's the root of 4 times 20, which is equal to 2 root 20. That's good. We did simplify it, but it's not completely simple yet. We're not done. So how do you know when you're done? You just have to keep checking. Hopefully the number starts getting small, so there's not actually that many numbers to check up from up on the board. There's only so many there, and they really get big very, very fast. So, but 20 in this case isn't done. It can divide by 4 again. So we would say that's equal to 2, 4 times 5, 2 root 4, 5. And then the 4 can be square rooted and pulled out. So it's actually 2 times 2 times root of 5, which is 4 root 5. Now you're not going to write all these steps, but if you didn't recognize that can be divided by 16, you'd pull out the 2, but then you'd pull out another 2, and you realize it's 4 root 5. So it doesn't matter if you find the best number, as long as you keep going and don't stop till you're actually done. But if you found 16, you get to that number right away. The minus came from the minus that's already there. And 2 root 12, well, that actually divides by, that's 4 times 3. So we're pulling out a 2. So again, it multiplies by the coefficient, and we left behind a 3. Now we have to talk about like terms. So we have like terms in the orange here. They're like our bags of marbles. So you had 3, but then you lost 4. So you're at -1 bag of marbles. And then we got the red guys, and these have the same variables, and these are like our bags of candy. So you owed somebody 3 bags of candy, and then the next day at school you owed somebody else 4 more bags of candy. So you owe 7 bags of candy now. You're really not a popular guy at school today. Okay, that's probably the hardest stuff. Let's try the backside. These 2 questions actually aren't too difficult. I want you to try them on your own first. You can pause the video. Okay, first one, I'll talk through it, then I'll just show you the solution. You're going to pull out the 4. You can't do anything with the C. In this side, you're going to pull out the 9. You can't do anything with the C. So you're going to take the square roots of them, so it's going to be a 3 joining the 4, and it's going to be a 2 joining the front. Now these are like terms, so you can combine them together. Not too bad. Same thing over here. The 20, we're going to pull out the 4, and we're going to leave the 5. 45, we're going to pull out a 9. This is actually 9 times 5. So we pull out the 9, which is actually a 3 on the outside, but 3 times 3 makes 9. And we leave a 5 behind, and now it's like terms again. So you had 2 bags of candy, and you lost 9 bags of candy. So again, you owe 7 bags of candy. Okay, are there any restrictions on the C value in this one? Yeah, it's a square root. So C has to be positive, or 0. Greater than or equal to 0. That's it for that. You just can't have a negative value for C. What about in this one? So again, it's the square root, so the radicand, 5x, has to be greater than or equal to 0. Divide by 5, so x has to be positive. As long as x is positive, this whole thing will be fine as well. Not too shabby. All right, the hard question. Only 14 minutes in. We're doing pretty good this time. What's the exact distance across the base in this question? Pin this back a bit. Okay, so we have this design for a skateboard ramp. I guess they're probably skating up the big side, and then they jump down the small side. We want to know the exact distance across this bottom here. And there's actually a lot of different types of questions that kind of look like this, and in a lot of different units. One type of question that's going to look like this is going to be a system of equations. It won't look exactly like this, but it might have the same kind of design, and it will end up being a system of equations. You'll have one equation for a variable over here, one equation for a variable over here. You'll write them beside each other, and you'll have to, the trick would be you have to use the same variable somehow, and then you'll sub them into each other and eliminate, or eliminate, and solve for the variable. And I've seen those type of questions. They're a bit challenging. I think we saw some like that in the trig unit. Another type of question that you can see with this one, and this is what I thought it was at first, is Pythagorean theorem. So you have to do two types of Pythagorean theorem, but you have to give your answers with exact values, so using square roots. And I thought that was going to be the case because we are on the square root unit, but we actually don't have any of the right information to do the Pythagorean theorem. You need two given lengths to use Pythag, and we only have one here. So Pythag isn't actually going to cut it for us. Hopefully you guys are looking at this question and you're saying this must be a trig. That's really what I want you to get to. There's so many different ways to look at triangles, especially now that you have all your trig skills. But the trick is, well, I think everyone can recognize when it is a Pythag one. To recognize when it's a trig one, you have one length, one angle, and you're looking for a length. So 3 pieces of information is classic trig, where you're looking for one of them. Either you're looking for the angle and you have 2 lengths, or you have a length and an angle and you're looking for the other length. So this is classic trig. Write out your 2 triangles. You don't have to necessarily, but it is good to kind of see them separately. And then we define our variables. So we care about the bottom. This x value is the bottom from here to here, and this y value is the bottom from here to here, or wherever this ends is kind of cut off. Now, write your equations. These are tans. So tan of 30 is opposite over adjacent. Again, tan of 30, opposite over adjacent. So we got all that. Now at this point, you might be thinking back to grade 10 when you still liked trig and you didn't have to deal with exact values. And you'd say, hey, I could solve this, but there's not going to be any square roots. It's just going to say x is like, I don't even know what x is going to be. I guess it's going to be bigger than 40. X is like 62.578 and y is like 32.578. So we know our answer is just blah, 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 whatever that adds to. And that could be true, but it's certainly not an exact answer. So where we get the exact answer and where we get the square roots from is our special triangles. So you group of superstars. Let's bring out our special triangles. This isn't going to be a 20-2 question because you guys never did special triangles. But actually, special note, 20-2, you will need to do exact answers in this chapter now. Just not with special triangles. You have to be able to simplify roots to their exact answer for root 5 and not just give me the number that root of 80 is. Okay, special triangles, it's 1 over root 3. We all remember how to draw that. This is our 30, 60, 90 triangle, and that's a 1, 2, root 3 triangle. So the longest length is 2, the middle one is root 3, the short one is 1. So tan of 30, O over A, 1 over root 3. So we get 1 over root 3 is equal to 40 over x, and we rearrange to solve for x. We get the same thing on the right, and we rearrange to solve for y. And then at this point, it's actually a really easy question. So we said x is 40 root 3, y is 30 root 3, and our total distance is just x plus y. So it's 40 plus 30, root 3's. So our exact answer is 70 root 3. Good. 20-minute video. That's not too bad. So in total, I held you up for less than 50 minutes. So you guys should still have about I don't know, 20, 30 minutes left in class. So for homework, we actually have two sets of homework, this one and the one from the previous section. And over the break, I don't think many people got very far into it, try those first 2 pages. Try to remember all the square root stuff from previous years. So we do have some work over the break. After the break, on the Tuesday when we get back, there's going to be a quiz on the first 2 sections, not these first 2 lessons. So all of this and one more, what we learn on Monday. And then the test is going to be on that Thursday. So the test actually comes up really quickly. So make sure you do actually go over this homework and try some of the practice stuff, the warm-up stuff, over the break. Okay, good luck.